In the flight plans for pilots, it is important that the route that they log with the control tower that they plan to follow be a continuous line, or in mathematics what we would call a continuous function. Hi, my name is Jason Rosenberry, and that's what we will be learning about in today's lesson, continuous functions and composites. Let's start with the definition. Definition: continuity at a point. Interior point. A function y equals f of x is continuous at an interior point C of its domain if the limit of f of x as x approaches C is equal to f of C. Endpoint. A function y equals f of x is continuous at a left endpoint A or is continuous at a right endpoint B of its domain if the limit of f of x as x approaches A from the right equals f of A, or the limit of f of x as x approaches B from the left is equal to f of B, respectively. Let's try an example. Find the points of continuity and discontinuity of the function. Identify each type of discontinuity. Our function is f of x equals square root of 2x plus 3. Let's first start by finding the domain of our function. The domain of function f would be the interval from -3/2 to positive infinity. The function is continuous on every point from -3/2 to positive infinity, so it's continuous throughout the entire domain. However, there are some values of x where the function is not continuous, meaning the function is not defined. So any value of x less than -3/2 would be a place of discontinuity. We carry this continuity at a point idea to a function over a whole interval as follows. A function is continuous on an interval if and only if it is continuous at every point of the interval. A continuous function is one that is continuous at every point of its domain. Let's try an example. Given f of x is the following piecewise function: 3 minus x for x less than 2, x over 2 plus 1 for x greater than 2. A. Find each point of discontinuity. B. Which of the discontinuities are removable, not removable? Give reasons for your answers. Here we have the graph of f of x. We see that this graph is discontinuous at x equals 2, and it's not removable because the one-sided limits are different. The limit as x approaches 2 from the left is positive 1. The limit of f of x as x approaches 2 from the right is positive 2. So this has jump discontinuity because it literally jumps between two different one-sided limits. There is also infinite discontinuity, where one or both of the one-sided limits are infinite, and there is oscillating discontinuity, where the function value oscillates too much to have a limit. There are some properties of continuous functions that are useful to note. Let's take a look at them. Properties of continuous functions. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c. Number 1, sums are continuous. Function f plus function g. Differences are continuous. F minus g. Products are continuous. F times g. Constant multiples are continuous. K times function f for any number k. Quotients are also continuous. F divided by g provided that g is not equal to 0. There is one other algebraic way to combine continuous functions. Let's take a look at it. Compositive continuous functions. If f is continuous at c and g is continuous at f of c, then the composite function f of g is continuous at c. Theorem 8, the intermediate value theorem for continuous functions. a function y equals f of x that is continuous on a closed interval from a to b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in the interval from a to b. Here's a graphical representation of this. Again, we know that y equals f of x is a continuous function. Basically, let's say call out a closed interval from a to b. So here I am from a to b. Here we are at f of a, f of b. So what basically this function says is pick any range value, pick any y value between f of a and f of b, call that y sub 0. Knowing that the function's continuous, that must imply then that there is this value c in the interval from a to b that causes the function value to be between f of a and f of b. Let's try an example. Is any real number exactly 1 less than its cube? In order to answer this question, we must solve the equation x equals x cubed minus 1. Again, we're trying to find, is there a real value or a real number x such that x is equal to x cubed minus 1. Setting this equal to 0, we would get the equation x cubed minus x minus 1 is equal to 0. So we want to know, is there any value of x out there that would cause the second equation to equal 0? So looking at the graph of x cubed minus x minus 1, we see that it changes sign between positive 1 and positive 2. Again, if we look at x equals positive 1 and x equals positive 2, we see that the graph is switching from negative values to positive values. So using the intermediate value theorem, we know, and because this function is continuous, we know there must be a value of c between 1 and 2 where f of c is equal to 0. Using the 0 function on your calculator, we can see that that true x value that causes the equation x cubed minus x minus 1 to equal 0, x is 1.325. So the answer is yes, there is a value of x such that it's exactly 1 less than its cube. Now it's time for you to try a problem. Is any real number exactly 2 more than its cube? Give any such value accurate to 3 decimal places. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. To solve this problem, we need to solve the equation x equals x cubed plus 2. Setting this to 0, we get x cubed minus x plus 2 is equal to 0. Now let's take a look at the graph of x cubed minus x plus 2. And we can see that between x equals negative 1 and x equals negative 2, this graph is changing from something positive to something negative. So there must be a value of c between negative 2 and negative 1 that causes f of c to equal 0. Using the 0 function of your calculator, we see that that x value is negative 1.521. In this lesson, we explored continuity, discontinuity, and how to apply these concepts to graphs. Be sure to work the exercises that your teacher assigns, and we'll see you next time.